We've all seen those cancer warning labels, right? But have you ever really stopped to think about what's happening at the molecular level, like when something from cigarette smoke actually interacts with our bodies?
It's fascinating, isn't it? And
Yeah.
surprisingly often, it comes down to the chemistry of these, well, high-energy compounds called epoxides.
The epoxides. Okay, so that's a great place to start.
Exactly. These epoxides and their cousins, ethers, plus their sulfur versions and vials and sulfides, that's what we're diving into today. Think of this as your shortcut through a pretty dense but really important chapter from Klein's organic chemistry.
Right. Our mission here is to pull out the absolute must-know stuff, the key insights, and make these, let's be honest, sometimes tricky concepts really clear and relatable for you.
And these aren't just abstract textbook things.
Mhm.
They pop up everywhere.
Yeah, I was surprised. Like painkillers, sleep aids.
Industrial solvents, even fundamental processes inside our own bodies. So, for everyone in our last-minute lecture family, let's get into it. Let's unpack this chapter.
Okay, first up, ethers. What exactly are we talking about?
Simply put, an ether is just an oxygen atom bonded to two R groups. And those R groups can be alkyl chains, aryl rings, even vinyl groups. Oxygen acting as a bridge.
And it's wild how many everyday substances, natural and synthetic, have this ether structure.
Totally. Think about natural stuff like morphine, the opiate analgesic,
Hmm.
or melatonin, the hormone that, regulates sleep.
Even vitamin E, the antioxidant.
Vitamin E2, yep, has that ether linkage. It's really fundamental.
And in medicines.
Oh, definitely. You've got R-fluoxetine, which most people know as Prozac, tamoxifen, used for breast tumors, propranolol for high blood pressure. All of them use that ether group in their structure.
Okay, so if you're looking at one, how do you actually name it? Seems like there are a couple of ways.
There are. The common naming system is usually pretty straightforward. You just identify the two R groups on either side of the oxygen, list them alphabetically, and slap ether on the end.
Like ethyl methyl ether.
Exactly. Or diethyl ether. Oh, and a quick tip, if you have a tert-butyl group, remember to alphabetize it under B, not T. That catches people sometimes.
Got it. But what about more complicated ones?
Right. For complex structures, maybe with lots of substituents or, crucially, chiral centers, you really need the systematic IUPAC naming.
Okay, how does that work?
You pick the larger or more complex R group as the main chain, the parent alkane. The smaller group, along with the oxygen, becomes an alkoxy substituent.
So like methoxybenzene instead of methylphenyl ether?
Precisely.
Ah.
Or for something really complex, maybe like R11 dichloro-3-ethoxycyclopentane.
Yeah. Yeah, systematic is the only way to go. Knowing when to use which system is a key problem-solving skill from this chapter.
Makes sense. All right, structure and properties, why are they such good solvents? That seems to be a major use.
It is. Structurally, the oxygen has that bent geometry, kind of like water or alcohols, but the bond angle is usually a bit wider because the R groups take up more space.
And how does that geometry affect things like boiling point? Significantly. See, alcohols can hydrogen bond with each other. That OH bond lets them donate and accept H bonds. That holds them together strongly, giving them higher boiling points.
But ethers, they only have CO bonds, right?
Exactly. They have that oxygen, so they can accept hydrogen bonds for something like water or alcohol, but they can't donate H bonds to other ether molecules. No OH.
Ah, okay, so they don't stick together as strongly.
Right. Which means much lower boiling points compared to alcohols of similar size. Think about dimethyl ether. It boils way down at negative out of 5 Celsius. Its isomer, ethanol, boils way up at 78 Celsius.
Wow, that's a huge difference, almost 100 degrees. So how do they compare to something totally nonpolar like propane? They must be somewhat similar.
Pretty close, actually. Dimethyl ether's boiling point is just a bit higher than propane's, which is negative 42 C. That small difference comes down to the ether having a net dipole moment because of the bent shape and the electronegative oxygen.
So weak dipole forces, which propane doesn't have.
You got it. And of course, as the alkyl groups get bigger, London dispersion forces increase and the boiling points go up, but still generally lower than comparable alcohols.
So that relative lack of reactivity plus the low boiling point for easy removal. That's why things like diethyl ether, THF, 1,4-dioxane are lab staples.
That's exactly why. They dissolve a lot of organic stuff, don't interfere much with reactions, and you can easily evaporate them away afterwards.
And diethyl ether used to be an anesthetic, right? Bit of history there.
It was a common inhalation anesthetic.
Yeah.
But it had side effects like nausea. So now we use halogenated ethers, things like ensilarine, azoflurane, sevoflurane, safer, better profiles.
How do those work, roughly?
The thinking is they probably disrupt synaptic transmission in the brain somehow,
Yeah.
maybe interfering with neurotransmitter release or binding, Adding those halogens really changes the properties.
Speaking of changing properties, crown ethers, these sound really
So
cool.
they are revolutionary. They're cyclic polyethers, multiple ether oxygens in a ring, named like X crown Y, where X is total ring atoms, Y is oxygen atoms, like 18 crown 6.
And what's so special about them?
Their structure. It's like a little crown, and the hole in the middle is just the right size to perfectly fit specific metal cations. The oxygens point inwards. They're lone pairs, stabilizing the positive charge.
Wait, so you can trap a metal ion inside?
Exactly. And this is the amazing part. It lets you dissolve inorganic salts, which are normally insoluble in nonpolar organic solvents, into those solvents.
Seriously, so you could take, like, potassium fluoride, KF, which hates benzene, and dissolve it using a crown ether.
Precisely. The 18 crown 6 ether wraps around the K plus ion, making the whole complex soluble in benzene. This suddenly makes the fluoride ion, F, available as a nucleophile in an organic solvent, which is normally really hard to do.
That opens up so many reaction possibilities, like using fluoride or permanganate in nonpolar conditions.
It was a huge deal. It basically launched the field of host-guest chemistry.
Yeah.
Charles Peterson, Donald Cram, and Jean-Marie Lannes won the Nobel Prize for this in '87.
Wow. Any links to biology?
Definitely. There are natural polyether antibiotics, like nonactin and monensin. They act as ionophores. They grab metal ions and shuttle them across cell membranes.
Disrupting the ion balance inside the cell.
Exactly. Messes up the cell's gradients, which kills bacteria. A biological molecular cage doing its job.
Okay, so we know what they are, some cool examples. How do we actually make ethers in the lab?
Well, industrially, you can sometimes make simple symmetrical ones, like diethyl ether, by dehydrating ethanol with acid. It's an SN2 process, but pretty limited.
What's the main workhorse method for synthesis?
That would be the Williamson ether synthesis. This is
Okay.
absolutely crucial to understand from this chapter. It's gold standard.
Okay, break it down for us.
2 steps. First, you take an alcohol and deprotonate it with a strong base to make an alkoxide ion. That's your nucleophile.
Got it, the RO minus.
Right. Then, that alkoxide attacks an alkyl halide in an SN2 reaction, kicking out the halide and forming the new CO bond of the ether.
Okay, SN2. That immediately rings alarm bells about the type of alkyl halide you can use, doesn't it? This is a classic spot where students make mistakes.
Absolutely critical point. Because it is SN2, it works best with methyl halides or primary alkyl halides.
Yeah.
Those are unhindered, good for SN2.
Secondary halides.
Less efficient. You start getting competing elimination reactions.
Yeah.
And tertiary alkyl halides. Forget it.
Why not tertiary?
Elimination completely takes over. The alkoxide acts as a base, pulls off a proton, and you just get an alkene instead of your ether. SN2 is too sterically hindered at a tertiary center.
So if you wanted to make, say, MTBE tert-butyl methyl ether, how would you plan that using Williamson?
Good test case. You must use tert-butanol as your alcohol, make the tert-butoxide ion, and react it with a methyl halide, like methyl iodide.
Not the other way around, like methanol and tert-butyl bromide.
Definitely not. That tertiary halide would just give you isobutylene via elimination. Choosing the right pair, which part is the alcohol, which is the halide, is key for Williamson.
Good tip. Any other ways to make ethers?
There's also alkoxymercuration demercuration. If you remember oxymercuration for making alcohols from alkenes.
Yeah, add water across the double bond.
This is the same idea, but you use an alcohol, ROH, instead of water. It adds the alkyl group across the alkene following Markovnikov's rule. Useful alternative sometimes.
Okay. Now what about reactions of ethers? We said they're pretty unreactive, hence good solvents.
Generally true, but not completely inert. The main reaction you need to know is acidic cleavage.
What happens there?
If you heat an ether with a strong concentrated acid, usually HI or HBr, you break the CO bonds and end up with 2 alkyl halided molecules.
How does that work? What's the mechanism?
It's usually a couple of steps. First, the ether oxygen gets protonated by the strong acid. That makes it a much better leaving group, turns it into sort of an alcohol-like group attached to an R group.
Okay, activates it.
Right. Then a halide ion, I or Br, comes in and does an SN2 attack on one of the carbons attached to the oxygen, kicking out the ROH part. Then that alcohol can react further with more HX to become another alkyl halide.
So SN2 usually. Is there ever SN1?
Good question. Yes, if one of the R groups is tertiary. That tertiary carbocation is stable enough that it might form first via an SN1 pathway after protonation, before the halide attacks. So mechanism can depend on the structure.
And what about phenyl ethers? Like anisole, methoxybenzene?
Special case. If you cleave a phenyl ether with HX, you get phenol and an alkyl halide. The phenol doesn't react further to form a halobenzene.
Why not?
Because SR1 and SN2 reactions just don't happen readily at sp2 hybridized carbons like those in an aromatic ring. The CO bond to the ring is too strong, and the intermediates are unstable.
Right, makes sense. And there was one other reaction, something about safety.
Yes, very important practical point. Autooxidation. Ethers react slowly with oxygen from the air. It's a radical process, forms unstable compounds called hydroperoxides.
Hydroperoxides. Those sound bad.
They are. They can be explosive, especially if concentrated. That's why old bottles of ethers, especially things like diacyl ether or THF that have been sitting around, can be extremely dangerous. You have to test them for peroxides before using them. Seriously, a major lab safety issue.
Good to know. Okay, let's switch gears to epoxides. You mentioned these earlier. Special kind of ether.
Exactly. They are ethers, but they're cyclic, specifically a three-membered ring containing oxygen, also called oxiranes.
Three-membered ring. That sounds strained.
Highly strained. That angle strain and torsional strain make epoxides way more reactive than regular acyclic ethers. That ring desperately wants to pop open.
How do we name them?
Two main ways again. You can name the oxygen as an epoxy substituent on a parent alkane chain, indicating the carbons it's attached to, or you can treat the three-membered ring itself as the parent, called oxirane, and name substituents attached to it.
And you mentioned a medical connection earlier, too.
Yes, the apothalones. These are natural products, originally found in bacteria, that have potent anti-cancer activity. Exabepilone is an approved drug for breast cancer based on this structure, and it features that key epoxide ring.
Fascinating. How do we make these strained rings?
Often from alkenes. A very common way is to use a peroxy acid, like MCPBA. This directly converts the alkene double bond into an epoxide.
And does it matter if the alkene is cis or trans?
Yes, crucially, it's a stereospecific reaction. A cis alkene gives a cis epoxide, substituents on the same side of the ring, and a trans alkene gives a trans epoxide. The stereochemistry is retained.
Okay, direct and clean another way.
You can also make them from halohydrons. Remember those, adding halogen and water across an alkene.
Right, X and OH on adjacent carbons.
Yep. If you treat that halohydron with a strong base, the base deprotonates the OH group, and the resulting alkoxide performs an intramolecular Williamson ether synthesis. It attacks the carbon with the halogen, kicking it out and closing the ring to form the epoxide.
Intramolecular, so within the same molecule. Clever.
It is. And interestingly, this two-step route gives the same stereochemical outcome as the direct epoxidation with a peroxy acid. So you have options depending on your starting materials.
So again, for synthesis problems, you need to look at the target epoxide, see the relationship between the groups, cis or trans, and work back to the right alkene.
Precisely. It's all about that retrosynthetic thinking. And just another connection, drugs like carbamazepine are metabolized in the liver partly by forming an epoxide, which is then opened by an enzyme, epoxide hydroxylase. Sometimes other drugs, like certain antibiotics, can inhibit that enzyme, making the original drug more potent because the epoxide hangs around longer. Drug interactions.
Wow, complex stuff. Now, what if you need just one enantiomer of a chiral epoxide? The methods so far give mixtures, right?
Right. They typically give racemic mixtures 50-50 of both mirror images if the epoxide is chiral. If you need just one specific enantiomer, you need enantioselective epoxidation.
How do you achieve that selectivity?
This is where K. Barry Sharpless made a huge contribution, earning him a Nobel Prize. He developed a catalytic system specifically for allylic alcohols. That's alcohols next to a double bond.
Okay, what's the magic?
It uses a titanium catalyst, titanium tetraisopropyloxide, along with a chiral ligand, either plus dis-det-Et or det-Et, which are chiral forms of diethyl tartrate. This whole complex creates a chiral environment around the alkene.
So the catalyst itself is chiral and influences which face of the double bond gets attacked.
Exactly. By choosing plus DET or DECT, you can selectively form the epoxide either from the top face or the bottom face of the allylic alcohol, leading to very high enantiomeric excess, mostly just one enantiomer. It was groundbreaking for controlling chirality and synthesis.
Incredible control. Okay, so we can make epoxides. Now, what about their reactions? You said they're reactive because of strain?
Right. That ring strain is the key driving force. They love to undergo ring opening reactions.
How does that happen?
Two main scenarios. First, reaction with strong nucleophiles. Things like Grignard reagents, alkoxides, cyanide.
Okay, what's the mechanism like?
It's basically an SN2 attack. The nucleophile attacks one of the carbons in the epoxide ring, and the CO bond breaks, opening the ring. The oxygen initially becomes an alkoxide O, which then gets protonated in a second step, usually by adding a weak acid workup.
And the SN2 part is important. Where does the nucleophile attack if the epoxide isn't symmetrical?
Crucial rule here, especially for problem solving. With a strong nucleophile under neutral or basic conditions, attack always occurs at the less substituted carbon.
Less substituted. Why?
Steric hindrance. It's just easier for the nucleophile to approach the less crowded carbon atom. Purely SN2 sterics.
And stereochemistry.
Inversion of configuration of the carbon that's attacked, just like any standard SN2 reaction. Backside attack.
Makes sense. Is this used practically?
Definitely. Ethylene oxide itself is used to sterilize medical equipment because it's great at alkylating biological molecules like DNA or proteins via this ring opening, which kills microbes.
Okay, that was strong nucleophiles. What's the other scenario for ring opening?
Acid-catalyzed ring opening.
Mm.
Here, you use a nucleophile, often a weaker one like water or an alcohol, but in the presence of an acid catalyst.
How does the acid change things?
The first step is the epoxide oxygen gets protonated by the acid. This makes the oxygen positively charged and turns it into a much better leaving group. It also makes the ring carbons more electrophilic, more attractive to the nucleophile.
Okay, activates the epoxide, then the nucleophile attacks.
Then the nucleophile attacks one of the carbons, opening the ring. Again, the oxygen gets protonated eventually if needed.
Now, the million-dollar question, regiochemistry. Where does the nucleophile attack here? Is it still the less substituted carbon?
This is where it gets really interesting and frankly a bit tricky for students. It depends.
Uh-oh. Okay, explain.
If you have a primary versus a secondary carbon in the epoxide, the nucleophile still attacks the less hindered primary carbon. Sterics still win in that case.
Okay, same as before.
But if you have a primary versus a tertiary carbon or a secondary versus a tertiary, the nucleophile attacks the more substituted tertiary carbon.
Whoa, hold on. Why the flip? Strong nucleophiles go less hindered. Acid catalyzed with a tertiary center goes more hindered. That seems counterintuitive. What's going on?
It is counterintuitive at first glance. The difference is the protonated intermediate. When that oxygen is protonated, it starts pulling electron density away, giving the ring carbons some partial positive carbrication-like character.
Okay.
A tertiary carbon is much better at stabilizing that developing positive charge than a primary or secondary carbon. So even though it's more hindered, it has more positive character, making it electronically more attractive to the incoming nucleophile. It's a competition between sterics and electronics. And with a tertiary carbon under acidic conditions, the electronic effect favoring attack at the more substituted site wins out.
Wow. Okay, that's a subtle but critical distinction. Sterics dominate for strong nu attack. For acid-catalyzed, sterics dominate primary-secondary choice, but electronics dominate if a tertiary site is available.
You've got it. That's a really key takeaway from Klein on epoxides. Stereochemistry, by the way, is still inversion at the site of attack.
And this acid-catalyzed opening is used industrially.
Big time. The production of ethylene glycol antifreeze is done by the acid-catalyzed ring opening of ethylene oxide with water. Huge scale.
And let's bring it back home. The cancer connection.
Right. Back to benzopyrene from smoke. It gets metabolized in the body, first forming an epoxide. That epoxide gets opened by water, catalyzed by an enzyme, to form a diol.
Then it gets epoxidized again.
Yes, forming something called a diol epoxide. And that molecule is the real villain. It's highly reactive and readily alkylates DNA bases through epoxide ring opening. That DNA damage can lead to mutations and, ultimately, cancer. A sobering example of epoxide reactivity in biology.
Definitely puts those warning labels in perspective. Okay, quickly then, let's touch on the sulfur analogs, thiols and sulfides.
Right. Thiols are just sulfur versions of alcohols. They have an SH group called a thiol group or sometimes mercapto group.
Or capto, like capturing mercury.
Exactly. Thiols bind strongly to heavy metals like mercury. Nomenclature is similar to alcohols ending in -sil.
And the smell.
Oh, the smell. Thiols are infamous for strong, often really unpleasant odors. Skunk spray is mostly thiols. They add tiny amounts of methanethiol to natural gas so you can smell leaks.
How are they made?
Usually SN2 reaction of NaOH, sodium hydrosulfide, with an alkyl halide. HS is a good nucleophile, but not a very strong base, so it works pretty well.
And reactions.
The main one is oxidation. Thiols easily oxidize to form disulfides, RSSR, linking two sulfur atoms. And disulfides can be easily reduced back to thiols. This disulfide bridge formation is super important in protein structure, holding protein chains together.
Okay, and sulfides, sulfur ethers.
Yep, RSR, also called thioethers. Naming is similar, using sulfide or alkylthio. You can make them by a sulfur version of the Williamson synthesis react of the thiolate ion, RS, with an alkyl halide, SN2 again.
Are they reactive like ethers? Or different?
They are a bit more reactive. The sulfur atom is a better nucleophile than ether oxygen, so sulfides can actually attack alkyl halides themselves to form sulfonium salts, R3S+, which are good alkylating agents. SAM, S-adenosylmethionine, in our bodies works this way.
Interesting. What else?
Sulfur can be oxidized. Sulfides can be oxidized first to sulfoxides like DMSO, dimethyl sulfoxide, which have an SSO group, and then further oxidized to sulfones, RSO2R. You control the oxidation level with the choice of oxidizing agent.
The SO bond, is it a true double bond?
Not really. Sulfur's 3p orbitals don't overlap well with oxygen's 2p for pi bonding, so it's more like a coordinate covalent bond with significant polarity. Oh, and sulfides like DMS can also be used as reducing agents, for example, in ozonolysis reactions.
Got it. Okay, last big topic, synthesis strategies. How do epoxides fit into planning a synthesis?
This is where they become incredibly powerful tools. Here's a huge tip from Klein. Whenever you see two functional groups on adjacent carbons, you should think of epoxides.
Adjacent functional groups,
Right.
like an alcohol next to a halogen or an alcohol next to an amine.
Exactly. Or an alcohol next to another OR group, or next to a carbon group added by a Grignard. You can often make that target molecule by opening a suitable epoxide precursor.
So work backwards, retrosynthesis.
Precisely. See the product with adjacent groups. Imagine disconnecting it back to an epoxide. Then think how to make that epoxide from an alkene. For instance, if you need an OH and an ON group next to each other, you could plan to open an epoxide with methanol under acidic conditions.
Controlling the regiochemistry based on those rules we just discussed?
You got it. And one more really neat trick involves Grignard reagents.
Okay.
When a Grignard reagent attacks an epoxide, it adds its carbon chain, and the OH group ends up on the carbon next to where the new CC bond formed. So the OH is on carbon, #2 of the piece you added.
How is that different from a Grignard attacking, say, an aldehyde?
Ah, great comparison. When a Grignard attacks an aldehyde or ketone, the OH group ends up directly on the carbon where the CC bond formed carbon, #1 of the added piece.
So attacking an epoxide puts the OH one carbon further away than attacking a carbonyl.
Exactly. It gives you different connectivity.
Yeah.
So a key skill is training your eyes. Look at your target molecule. Where is the OH group relative to the new C-C bond you need to form? If it's on C1, think carbonyl. If it's on C2, think epoxide. It's about choosing the right tool for the job.
That's a fantastic synthesis planning tip. Really makes you look closely at the structure.
It's all about that careful analysis.
Oh, okay, wow. Let's try to unpack all of that. We've covered a lot of ground here. Ethers, epoxides, thales, sulfides.
Yeah, from basic structure and naming through their properties like boiling points and solvent uses.
To their reactions, Williamson synthesis, acidic cleavage, the crucial epoxide ring opening rules, both nucleophilic and acid catalyzed.
And those sulfur analogs. And finally, how epoxides are such versatile building blocks in synthesis. We hit those key concepts from Klein pretty hard.
So what's the big picture takeaway for you listening?
I think it's amazing how small structural features like having oxygen versus sulfur or having that intense ring strain in an epoxide can lead to such massive differences in reactivity and function.
Yeah, it shapes everything from how well a solvent works to how a drug functions, how proteins fold, and even, disturbingly, how something like cigarette smoke can lead to cancer.
It really makes you wonder, doesn't it? What other things that happen around us or even inside us are governed by these kinds of subtle but powerful chemical principles?
Definitely something to think about. Keep asking those why and how questions as you study. We really hope this deep dive was helpful for everyone in our last-minute lecture family tuning in. Thanks for joining us.